Good morning class and welcome to our continuing lectures on sustainable energy technology. We had been discussing electrochemical energy storage, that is battery storage technology, in the last few classes, and we will continue our discussion on that topic. So today we will start our discussion on several different types of batteries that there are in usage in today's world, and what are their specific advantages and disadvantages, what materials they are using and where they are specifically used. First, we will start our discussion with the most earliest form of rechargeable battery system, which is lead oxide battery storage technology, which is commonly known as lead acid battery. So here, one of the electrodes, the metal electrode is lead and the metal oxide electrode is lead oxide. It's the oldest and the most widely used type of rechargeable battery in usage today, and it is very frequently used as a car battery for the startup of a car. So if you have an experience of driving a car or being in a car, you would know that initially the car requires a button or a key to start, and there is much before we went to electric vehicle systems, all car engines had a battery that was used to kickstart the car engine. Specifically, this is used for spark ignition type of car engines, IC engines, where an initial spark is required to ignite the fuel in the cylinder chamber of the car engine. And this spark was given by a battery system, and that car battery is typically a lead acid battery. It is also used for emergency power backup. So for example, battery based UPS, battery based inverters, etc. traditionally and even today uses lead acid based battery packs. And it has also been used in many places as storage solutions for renewable energy grid systems, distributed energy storage solutions, etc. So it is the most widely deployed form of battery technology today, apart from in the electronic applications, and it has widespread uses from car engines to energy storage in grids and distributed locations, for emergency power backup, etc. So as discussed, one electrode is metallic lead while the other electrode is lead oxide, PbO2. The electrolyte traditionally is dilute sulfuric acid, H2SO4 solution, which is basically a mixture of H plus ions and HSO4 minus ions. Okay, so hydrogen ions, positive hydrogen ions, and HSO4 minus negative ions. Okay, so electrolyte is sulfuric acid, which breaks down into H plus and HSO4 minus in solution. So the reactions that typically occur during the discharge process, so remember in the recharging process the opposite reaction will occur in each of the electrodes. So in the negative electrode side, remember that the negative electrode is the donor of electrons to the external circuit during the discharging process. So here we are getting the dissociation reactions that are happening. So lead and HSO4 minus ions that are coming from the electrolyte are coming together to form lead sulfate, H plus and 2E minus. Okay, so here what we are seeing is the HSO4 minus ions that are present in the electrolyte are being absorbed on the electrode surface, and lead sulfate is being produced from lead, and H plus ions are generated that are going into the solution, and 2 electrons are generated that are going into the circuit. Okay. In the positive electrode, the lead oxide electrode reacts with the H plus ions that are traveling from the negative electrode side towards the positive electrode side, and are combining with the electrons coming from the external circuit and the HSO4 minus ions that are also present in the solution. So all of these ions are interacting with the lead oxide material in the electrode to form lead sulfate and 2H2O. Okay, so here a recombination reaction is being produced where you are getting neutral molecules from ions. Okay, and as we discussed, during the charging process, the reverse reactions are happening at each of the electrode sites. So the energy released per electron in the lead dioxide to lead sulfate reaction at the positive electrode exceeds the energy consumed per electrode in the lead to lead sulfate reaction at the negative electrode by 1.5 electron volts. So the EMF is 1.5 volts. Okay, so basically this is the energy difference between the energy released and the energy consumed in terms of electron volts. It's a unit of energy. Basically it's a very small unit of energy. It's the energy gained by an electron as it goes up a potential gradient of 1 volt. Okay, so that's the unit of energy here. It's 1.5 electron volts. So the EMF is basically divided by the charge of the electron. So the EMF is 1.5 volts. Okay. So this is the typical EMF of a lead oxide battery. And you can see this aspect previously also, that the EMF of a lead oxide system is typically small. So we saw now 2 classes ago now. In this chart here, you can see the lead oxide is around the 1.5 electron volt region. Okay. So some modern designs, so typically aqueous sulfuric acid solutions were used, but modern designs try to go into dry cell batteries, where instead of aqueous solutions which are vulnerable to leakage, etc., you are producing pastes of the electrolytes. So paste filled electrolyte matrix, electrodes with high surface area. So you create specific electrodes which has porous surfaces, so increasing the surface area for the reactions to occur. You are using paste instead of aqueous electrolytes. So these kinds of advancements can generate battery currents of the order of 250 amperes. Okay, so lead acid batteries can generate a high amount of current. Okay, and hence lead acid batteries are good as startup batteries for heavy machinery. It can generate, so its power generation capacity is quite large, even though the efficiencies at high power points are usually low, but they are very good as startup batteries for heavy machinery. So starting up of car, as in spark ignition engines, or starting up of motor specific machineries that require an initial push for energy, that can be given by lead acid batteries, as well as we saw supercapacitors. So before the invention of supercapacitors, lead acid batteries were the go-to technology's choice for startup based systems, where they are injecting energy to overcome the initial resistance and inertia in heavy machineries. The theoretical specific energy values are around 200 watt-hour per kg. So theoretically it could store up to 200 watt-hours of energy per kg of the battery material. However, 38% of the electrolyte is water, so it's not concentrated sulfuric acid. You must have 38 to 40% of the solution as water. So, and that water actually does not take part in the reaction, so it adds to the inert weight of the battery. Also, lead is a very heavy element, so actually achievable specific energy densities are significantly low, around 35 watt-hour per kg. Okay, around like specific power values of 5 watt per kg, you will get mass specific energy storage capacity of around 35 watt-hour per kg. So as we discussed, the amount of power you are supposed to deliver to the external circuit, that also determines the mass specific energy density of the battery storage system. So at 5 watt per kg power delivery rate, your energy storage capacity is around 35 watt hour per kg. Okay. At higher power, specific energy density can be even lower. So if you are going for power generation of 100 watts per kg, so significantly high values of power delivery, then the specific energy density can go down to 25 to 20 watt hour per kg. Okay. So this is something again we saw in the previous classes, that if you increase the power output, then the energy storage capacity decreases. Now the reason why is this happening is, at high power output, lot of the energy is wasted as heat, and chemical irreversibility rises with faster reaction rates. So remember, in a battery what we are having are chemical reactions. As the speed of the chemical reaction increases, the reactions move away from thermodynamic equilibrium. So the irreversibilities associated with the reaction process through heat losses, leakage, etc. are going to increase. So as the reaction rates increase, as is needed at high power delivery rates, the reactions become less thermodynamically efficient, and hence the power storage capacity per unit kg of the material decreases. Okay. And lot of that power loss is basically wasted as heat and chemical irreversibilities. Okay. Now lead oxide batteries usually last for around 800 cycles. So this is also an important point. Unlike capacitors and supercapacitors that can last for millions and hundreds of millions of cycles, the lifespan of typical batteries are quite low, around 800 cycles, etc. So they have a short lifespan before they have to be replaced. And this is again because you are having chemical reactions, heat generation, etc. that slowly but irreversibly degrade the structural integrity of the electrodes. Remember, the electrode material itself is changing during the charging and the discharging processes. And as the material changes, it changes the crystal structure, or the material structure itself starts to get stressed as it changes back and forth from one type of molecule to another type of molecule. So with increasing cycles, the material structure of the electrodes degrade, lead dendrites and protrusions may form in the electrolyte. So the electrolyte surface no longer remains smooth, but there can be lead dendrites or protrusions happening that are extending into the electrolyte system itself, increasing short circuit hazard. So basically, if the two electrodes make direct electrical contact due to the presence of creation of protrusions from both sides, then the battery system gets short circuited, right? Internally short circuited, and it can no longer act as efficient energy storage systems. Okay. So if the electrons find a way to move from the anode to the cathode directly, right, without going to the external circuit, then the battery becomes useless. Further, with larger cycle times, lead sulfate crystals cover the electrode material, reducing active area. So as the cycle times increase, not all of the lead sulfate gets converted back into lead during the recharging process, and the excess lead sulfate starts to cover the active lead material and the lead oxide material, reducing the active area of the electrodes. Okay. And it also has reasonably low cycle efficiency of around 0.5 to 0.9. Okay, so the cycle efficiency is at the lower end for these kinds of electrochemical cells. Another issue is lead and sulfuric acid are toxic and has environmental problems unless properly recycled. Okay. Lead is a heavy metal, certainly toxic. Sulfuric acid is of course extremely dangerous to skin and to human health. Okay, so the battery materials are quite toxic, and it requires the recycling and the management of the battery material is essential to make this a sustainable energy storage system. So typically people want to move away from lead oxide batteries despite its long use and established technology present because of these problems, not least the environmental sustainability issues of using lead and sulfuric acid in the first place. Okay. The next type of battery that we will discuss today is the nickel cadmium battery. Okay. This is also a reasonably established battery technology and is primarily used for electronic systems. Okay. It has a EMF of 1.2 volts. So basically the energy difference between the energy released versus the energy consumed is 1.2 electron volts. So the EMF is 1.2 volts. The specific energy density is 40 to 50 watt hour per kg under practical conditions. So clearly its energy density is higher than an acting lead acid battery. You are getting 40 to 50 watt hour per kg of energy density. So you can get away with lighter batteries delivering the same amount of energy. Okay. Here the negative electrode is finely dispersed cadmium and the positive electrode is nickel oxyhydroxide. Okay. So the negative electrode, which is the source of electrons during the discharge process, is the metal cadmium, and the positive electrode is the nickel oxyhydroxide. Okay. This is also a pair that we discussed earlier, nickel oxide versus cadmium. Okay. The electrolyte between them is a polypropylene fleece. So again a kind of a polypropylene matrix which contains 20% potassium hydroxide solution. Okay, so it's again we are looking at a dry cell battery with kind of a polypropylene matrix in which the electrolyte liquid is 20% potassium hydroxide solution. Okay, so instead of sulfuric acid we are using potassium hydroxide. Okay, so the reactions during the discharge of this battery, if we look at the two sets of reactions, one is with the negative electrode, that is the electron donor during the discharge process, cadmium and the hydroxyl ions that are present and a result of the dissociation of potassium hydroxide come together to form cadmium hydroxide and 2 moles of electron. So the ions from the hydroxide ion, the hydroxide of the hydroxide ion reacts with cadmium to form cadmium hydroxide and the charge becomes free, so you get 2 atoms of electron, and this is going to the external circuit. Okay. In the positive electrode side, the nickel oxyhydroxide reacts with the water that is present in the electrolyte and the 2 moles of 2 atoms of electron that is coming from the external circuit to form nickel hydroxide and 2 moles of OH minus ions. So here we see a difference. Instead of the transport of positive ions from the negative electrode side to the positive electrode side through the electrolyte, we see a transport of negative ions, basically the hydroxyl ions, which are generated in the positive electrode side and are getting transmitted to the negative electrode side. The direction of the current is the same. Instead of a flow of positive ions this way, you are getting the flow of negative ions this way. Okay, the same idea comes. So the negative ions react with cadmium to produce cadmium hydroxide and 2 atoms of electron, while in the positive electrode side, the nickel oxyhydride reacts with electrons and water to form nickel hydroxide and 2 atoms of OH minus ions. Okay. So the total reaction is cadmium plus nickel oxyhydroxide plus water equal to cadmium hydroxide plus 2 nickel hydroxide plus energy. Okay, and that energy gives you the EMF of 1.2 volts. Now the problem here is this kind of a battery has very low cycle life, around 100 to 200. So this is not very useful for what you would call renewable energy grids or where more frequent cycle lives are necessary. Another problem is cadmium is a toxic substance and efforts are ongoing to phase out the cadmium nickel batteries. So cadmium is also extremely toxic to human health. So we are trying to replace cadmium with something more environmental friendly that has lower sustainability issues. Okay. These are used in electronic toys, electrical tools, emergency power, cameras, etc. So primarily household user equipment is powered by this kind of cadmium nickel batteries. Okay. So we will stop here today. In the next class, we will continue our discussion and we will look at other forms of battery, and certainly we will look into the very widely used and famous lithium ion battery as well. So thank you for listening, and we will see you in the next class. Thank you.